Hey there YouTube, this is SJM4306 back with another video. This time it's another project video. This video very helpfully has been sponsored by NextPCB. Okay, so yeah, I've played with these Eink displays or EPDs, electrophoretic displays, for quite a while. I have the small one here. I have like a large 4.3 inch one that's much higher resolution. And I've written my own library so that you can write to these displays without having to fully double buffer them. Because I like to use little tiny Arduinos like this guy. This is basically equivalently an ATmega 328P, basically an Arduino Uno. These only have like 2K of RAM, and when you have like a large display, like the 4-inch EPD that I have is I think 300 pixels by 400. That would, I just don't have enough RAM to buffer that entire display. Like I think I would need like 2 to 4 times as much RAM or something. I don't know. I could do the math, but I don't feel like doing math right now. Anywho, so yeah, so clearly using a lot of the stock libraries that these Eink display module manufacturers have put out, a lot of them require you to fully like double buffer the display. So that's not going to work for a lot of what I want to do. So basically what my libraries end up doing is buffering just a single line in order to write to for specific strings or graphic blocks, etc., etc. So in that way they can save RAM, and so in general that allows me to write to like a relatively large display without consuming a massive amount of RAM on the Arduino. This module is by Heltec. This is a 2.13 inch one, and this is 3 colors, so it can do black, white, and then red. You can see there's a little bit of red seeping through there. I currently don't have anything red on the display, and this has been obviously unpowered for quite a while, so the white is starting to turn pink. That's more only an issue with the 3-color EPDs. The pure black and white ones don't really have that issue, I found. Whatever you leave them at, they kind of just seem to stay that way forever. So, this project is actually not specifically about that display. It's about this one that I ended up getting, and this one is a let's see, can I see? I guess I'm gonna have to take this apart. Okay, so this specific module is it's from ByDisplay. Oops, upside down. ByDisplay.com. And the model number is EREPM0213-1. And I believe there's like a letter usually after that that'll specify whether this one is just black and white, but they also make black, white, and red, and black, white, and yellow as well. So there's basically like 3 types of these displays floating around. And so I got this module, and then NextPCB reached out to me. They asked me if I was working on any future projects, and I thought this would be a good time to get back into EPDs, and I wanted to make an actual clock. And so it was perfect timing. I designed up this board and sent it out to them, and I got the boards in, I soldered it, and then I noticed a major oopsie. Before I plugged it in, luckily I did check. Between the VCC and ground pins, there was a dead short. And it ended up being my footprint for the USB-C connector. I forgot to put isolation around the bottom pins there. I kind of do a not so smart thing of I do a ground pour on the top plane usually, and the bottom plane is VCC. Generally you would do ground on both and just run your VCC, but it makes it slightly easier to route. But in cases like this where you kind of make an oopsie and you accidentally bridge the 2 layers, you can get dead shorts. So what I ended up having to do is I took this to the CNC and the Vivor one that I reviewed in the past, and I just manually drew a box using the pendant controller, and it took 3 passes. I didn't go too deep each time. I only went like 0.1 millimeter depth, and it took 3 passes to get all the way through, undoubtedly because the board wasn't perfectly flat the way I clamped it. But yeah, especially since I had a bunch of junk on the other side. So it's kind of amazing that that worked. I measured now ground and VCC, and there was no longer that dead short on there. So yeah, double check your PCBs, I guess. That was definitely my fault. NextPCB followed exactly what I told them. I just very idiotically told them to short ground to VCC. But anywho, once I did that, I was able to plug it into like a serial programmer dongle that I have here, and I was able to flash firmware, and this board works perfectly. So one thing to note is these two displays look identical almost, other than, you know, the reddish color, but they use completely different controllers, and the code between these two are incompatible. So the next step is I actually had to write a firmware driver for this, the specific display driver, which I believe is like the SSD. I'll flash it down below here. But anywho, so I had to write a driver specifically for this. Okay, so we're all back together now. Before we get too far into deep of this specific module, which I'm calling the InkClock, very aptly named, the features of this board, which I haven't fully tested yet, I kind of want to go into theory of what an ink display is. Not everyone has used these or necessarily come across them in consumer products. If you've ever used like a Kindle with like a what they call the Paperwhite display, that is an ink display. And basically how this works is imagine a top layer and a bottom layer. And these are electrodes. And it's not necessarily just a full sheet of electrodes. It's actually arranged like a grid so that it can control, you know, multiple pixels underneath them. And imagine giant spheres of a viscous fluid. And what the colorant within the ink is actually a bunch of little balls within those. Those are pigment balls. And say this is white and this is black. So all the black ones are here, all the white ones here. They're charged differently. So say, I'm not sure what the convention is, but say the whites have a positive charge and the blacks have a negative charge. If we want the black pigments to float to the top, we have to apply a positive charge to the top terminal and a negative charge to the bottom terminal because opposites attract. And so these pixels will go up and these, well, pigments will flow down. And depending on the magnitude of the charge, as well as how long you let these float to the top or the bottom, you could also theoretically control like grayscale. So you can get different shades of gray in addition to black and white. Now the black, white, and red displays actually have a third type of pixel that's physically larger than the other two. So it'll be the same charge as the black, and these are red. And because of they're physically larger, it takes longer to flow to the top. So to control the red to the top, you put the positive charge on the top electrode for a longer amount of time, which brings all of the pixels up to the top, or pigments. I keep saying pixels. So it brings all the pigments up to the top, the pigmented balls. And then you quickly reverse the polarity on the top to drive the black towards the middle, in which case then only the red will be at the top. So that's generally how you control 3-color EPDs, or even more. There's now up to, I think, 7-color EPDs. The problem is adding these slightly larger balls increases the amount of time it takes to refresh the display. So for this black, white, red display, I think it takes like up to like 30 seconds, maybe 20 to 30 seconds to fully update the display. For the 7-color ones, I've seen it takes like significantly longer, like almost like a minute, something like that. But these black and white ones, because there's only 2 colored pigment balls, can update quite a bit faster on this display. You'll see in a second when I give you a demo. This only takes maybe about a second and a half, maybe about a second and a half to update the image, and it will flash a couple times because it's doing what's called a full refresh. So what a full refresh is it blanks the display first, and then it writes the new pixel data. And it does like an invert sequence in between, because if you were to just apply a static DC voltage, the display would work. It would bring the black pixels to the top and move the white pixels to the bottom. However, you can permanently charge the electrodes so that you'll get like ghosting, and if you leave that DC bias on long enough, you'll actually like polarize the actual electrode material or whatever the display is made of, and then you'll no longer be able to actually fully turn on or off specific pixels depending on how long and how hard they were driven. So that's why they drive this with sort of AC waveform in order to kind of equal out the charge, so that long term there's no charge that's built up inside of the plastics of the display. So yeah, and obviously each of these spheres isn't necessarily a pixel. You can have the electrode end at this point and have another electrode at this point within this sort of grid matrix, so that you can control half the pigments within one giant sphere and the other half in the other. So the pixel boundaries aren't necessarily limited to just the size of this larger capsule sphere. So yeah, that's generally the theory of how EPDs work. The controllers are like fantastically complex. If you ever get bored and you want to read a good data sheet, read a data sheet for one of these controllers, which I'll link the one down below that I'm using in this video. There's a lot of temperature relation. So a lot of the controller chips actually have a built-in temperature sensor. Because the viscosity of the fluid changes with temperature, it has to, if the colder it is, it has to take longer, it has to give the pixels longer to rise to the top or fall to the bottom. So it's temperature dependent. There's a built-in memory usually that has the waveform stored. So you can imagine it's driving these with some sort of square wave and these with the opposite polarity ones. But the timing and like the voltage levels, everything, all that's controllable within the controller in what's known as a LUT, a lookup table. And that's where the magic sauce of these displays lives, is in that lookup table. Contains like the optimal values in order to get the highest contrast and like the best looking display. And that's usually pre-programmed at the factory into the one-time programmable or OTP memory within the display controller. And that can only be programmed once as far as I know. And so that's not, you can't read that out normally as well. So it's programmed at the factory to work for that specific display over a range of temperatures. And so a lot of the magic in getting these displays to work correctly and reliably over a long period of time is in that you can't really get. You can go online and see for specific displays, some people have figured out waveforms that work, and they've done something really cool too. Applied Sciences did a video quite a while ago, actually, doing fast LUTs. He wrote his own fast LUT that would update the pixels faster at the expense of possibly polarizing the display. So it's okay to do that every once in a while, but like every, I don't know, 5 or 10 times, you really should do a full refresh to like equalize the charges on the display components. But that's one thing that I haven't quite gotten around to for my specific controller. I'm only doing full updates. I am going to work on doing partial updates so I can display things faster on the display, because like I said, I like to use this for a clock, but doing the full updates, it would take too long to set the time, because you have to wait every button press. You have to wait like a second and a half, 2 seconds, something like that, for it to update the display. So I'm definitely going to, for like a time set mode, I'm going to do a partial refresh. But during like the normal timekeeping mode, I'm 100% going to do full refreshes, because I want this display to last as long as possible with like minimal ghosting. You can see here, it actually does look very much so like paper, like its name implies. There is a protective sheet here. I'm just going to leave that on. It doesn't affect anything. But yeah, it looks really good. High contrast. The pixels, this is 212 by 104. And it's actually really sharp for what it is, and like super high contrast. It looks beautiful. I wrote a number of like weather symbols and Wi-Fi symbols because I originally intended this to be connected to the internet and retrieve the time and weather automatically once you connect it over Wi-Fi. I don't have the circuitry on this board right now to do that, but I did expose a I2C port and a serial port, so I could actually connect a third board in the back with Wi-Fi if I wanted to. But I was thinking of making this low power, and you can see the battery icons here, because I actually have integrated a TP4056 battery, lithium-ion battery charge controller, and a header that can connect a battery. I was thinking of extending this and this fits almost perfectly in 18650, so I could actually fit like a 2 or 3,000 amp hour battery on here, just making it a little bit thicker out the back, in between these two boards. Fit significantly larger battery than you would expect, and then have this, you can charge this over USB and then you unplug it and it continues working, and it would give you every maybe like once a day or twice a day, it would update the battery and show you how much charge is remaining. Like I said, these displays only take energy when they're updating, when they're changing. Right now, it's not even plugged in and the image is retained. So if I'm only updating this once a minute, this should consume, very little amount of battery power, and I could put the microcontroller to sleep the rest of the time. So that should be pretty good running off an 18650. It should last quite a while. So an issue I found with this specific display is the specifications, the documentation all say that it runs off of 3.3 and 5 volts. I can only get this to update effectively at 5 volts. So I don't have any boost regulation circuitry in here. It's powered straight off of a lithium battery. So that means the range will be like 3.5 to about 4.2 volts fully charged. And when I said it runs off the range of 5 volts about, it actually will run down to 3.6 or 3.7 volts, and under that, the display no longer responds. The controller I can communicate with, it's still running, but the display will stop updating if the voltage gets below around 3.6 volts. So what that means practically is when I go to make this battery powered, it'll really only use it'll use like at least half of the battery power, like stored it in a lithium battery, but it won't be able to run the battery down lower than that. It'll have to declare that the battery is dead at around 3.6 or 3.7 volts, leaving a bit of the energy in the battery on the table effectively. But that should actually kind of work in my favor as well. It makes it not run as long off of a single charge, but it also kind of protects the battery by not letting the voltage get too low before you have to charge it anyway, because the display no longer updates. And like I said, if I stick a decently sized 18650 in here, I don't think I'm going to have to charge this that often anyway. I have only so far validated the microcontroller and the display driver software. I haven't tested the RTC. I don't see, it's just an I2C DS3232MZ RTC. So I've written software for that before. I just need to actually implement it in the controller. The TP4056 I haven't tested either with the battery to verify if that works or not. That will be upcoming. That kind of stuff is going to take me a bit more time. I just wanted to show you guys because I just got the display driver working with my graphics library. So I have right now a USB-C cable going to my laptop. This is just for power, by the way. There's no data going to the USB connector, so you cannot program this controller over USB because I omitted the bridge chip. You have to use UART to program it, so you need a dongle like this to program it, basically. But let's just power this on, and so I have 3 buttons on the board and a blue blinky light. The red light is power. The orange light means that this is charging, but there's no battery. It thinks it's charging nothing, but just ignore that. If I plugged in a battery that was full, that would turn off. The blue light is blinking pretty furiously, and I have 3 buttons here. I have a 4th button, which is just a reset button for the main microcontroller in case it locks up or crashes. So I have 3 buttons here. The middle button will clear the display. You can see how long it roughly takes. It has to flash the display a number of times, and there, it's done. So yeah, that took about a little over a second. If I click these buttons are like previous page and next page, because I have 4 pages programmed. So if I go back to the first page, it displays the image that I showed you before with the battery icons and everything. I have my logo, so I can draw full bitmaps. I can draw, full screen update at once if I wanted to. I'm only drawing like little bitmaps and text. I've implemented an invert function so I can like select things on the display. I have multiple character fonts as well that are stored in Flash. And all these are basically bitmaps implemented into the Flash. If I click the next page button, you can see here more of those fonts I've mentioned. These are just for numbers specifically, but this is actually the font from a Sony mini, like a high-MD mini disc recorder. I really liked it. It looks really futuristic, so I actually took a picture of the screen and then magnified it, and then I drew out the bitmaps and I made my own number font from that. It looks really cool, kind of futuristic. This is just sort of a slightly larger version of like the 5x7 font from the previous page. And this is basically 7 segment. It looks actually pretty convincing as 7 segment. You can see though it's made out of like multiple pixels. So it's not really a segmented display. This is still a dot matrix display. And if I go to the next page, see the tiniest font that I have, like I mentioned, is 5x7. And you can see here, like you could store quite a bit of text. You could fit at least like almost 4, a little more than like 4 of these on the screen at once and have a little space at the bottom. If I go to the next page, I have more fonts. And this is a larger font, but not the largest I have. When I'm going to make this a clock, I'm going to have the digits be maybe a little bit smaller than the display and have like the calendar at the bottom. So it'll say like the day a week, the month, the day, and the year. But most of the display is going to be taken up with the actual current time. And what I'm going to have is a full menu system and whatnot. Once I get partial refresh working, I can make menus that you can actually navigate through in real time without having to wait like a second or two for the display to update. It'll be a little bit more fluid, so you can actually go through and increment things like almost instantaneously. But yeah, you can see this font's the same exact one that I put on this display, but it is obviously whiter just because this hasn't been refreshed in so long, so the red pixels are starting to float to the top, making the white look kind of pink. But yeah, okay, so this demo sketch with the buttons and everything and writing to the display is currently using 36% of about 32 kilobytes. There is a bootloader on there that uses about 2 kilobytes, so it's using about a third of 30 kilobytes. The RAM usage is only 21%-ish out of the 2K RAM. So I have most of my RAM still available, plenty enough to implement a simple clock. Overall, this project's going mostly how I wanted, with the exception of the voltage on this display not working down as low as I wanted to. People were saying on forum posts why this display can't be updated below about like 3.6 or 3.7 volts is due to there's a bidirectional level converter, like a level shifter chip, that this board is using so that you can drive it at a higher voltage. These displays, you can technically, they will work at 5 volts, but they're specifically designed for 3.3 volts, so you can actually potentially damage or shorten their life if you try to use them for 5 volts long term. So they put in that a linear regulator and that level shifter chip. But I think there's something funky going on with the level shifter chip where it'll stop working below like 3.6 volts for some reason, even though it's supposed to. I've looked at the data sheet for it. I haven't looked at how it's wired in here, but according to the data sheet, it should work down to like 2 point some volts on the lower voltage side. But for some reason, it's not on this board, and the way it's wired currently is it can only work down to like 3.6 volts. So once I get everything designed and working right as a clock, I might look into that and reverse engineer what the wiring on this board is. Then I might be able to figure out a way of modifying it to work down to like at least I would want it to work down to at least like 3.2 volts. So I can get almost all of the power out of a battery per charge to basically make this last as long as possible. Okay, I couldn't help myself. I was going to make it a separate video, me making a clock. I just went ahead and made a clock. It took me about a week. The software's not complete though. So this is just a basic functioning clock, but I don't have any advanced features like alarms or anything like that yet. But yeah, you can see it is currently updating. It is Easter. It's Sunday the 31st, and the time is correct. So it's about 3 p.m. So yeah, I currently have it soldered up just with a header so I could remove it to the two batteries that I pulled from a laptop. So this was a 6-cell. It was a series, 3 series, 2 parallel. And so I just took one of the segments. And so these are in parallel. So this is 3.7 volts at, I think 2200 milliamp hours each. So that's 4400. And at the current draw, I haven't optimized for battery consumption. So the microcontroller is always running. It's not actually sleeping. So it draws about 9.5 milliamps on average, like consistently. And it increases a little bit when it actually refreshes the screen, but not by that much, maybe like 1 or 2 milliamps. So as of right now, the way that this is programmed, this battery will last like maybe about 2 to 3 weeks on a full charge. By the way, I just tested the charge controller chip, and for a battery this large, like just under 5,000 milliamp hours, it takes forever to charge. It will take like an entire day. I have set the charge current on this chip here, the charge controller TP4056 to 1 amp. And so yeah, this will still take like, quite a while to fully charge. Overall, I have this main screen here programmed in. If it's between, I think like 6 a.m. to 6 p.m., it's not inverted. It's like this white background, black text. If you view it during the night, it'll automatically invert the display, sort of like that, where it's white text on a black background, just to show you that it's like night. I don't know. I'm going to have a setting that you can easily turn that on and off within the menu. You can see here the font for the text is actually decently large. I think it's 32 pixels high, so it's like almost half the screen is the time and then AM, PM. If you wanted to, it would be trivial to modify this to write 24-hour time instead of 12-hour. We have the day of the week, which is Sunday, and then the month, the day, followed by the year. And I have a tiny little battery icon here. I'm going to make that bigger. That's too small because it's difficult for me to see. And B, that's actually not, there's no logic behind that right now. It's just drawing a static icon. Actually, I have to implement reading the battery. So that should be fairly easy to do. I'm just going to use, there's an open source library for reading, microcontroller reading its own supply voltage. It basically uses the internal reference within the ATmega to back calculate that voltage. So I'm going to end up using that. I'm not writing that myself. I could, but I'd rather spend more time coding the UI. Also, you might have noticed there's a RTC battery, so it keeps time even if you unplug the battery or if the battery dies. So I put a little coin cell, a CR2032. It's just a primary cell, so I do have circuitry for charging other types of cells, but I don't actually have that wired or actually soldered in there rather. So this is just a primary cell. This will keep it for I don't know, probably a year or so. Even if it's totally dead, that'll keep time. We have the USB-C connector for charging, as well as if you just wanted to remove the battery and power this permanently off USB-C, that'll work just fine as well. We have 3 buttons here. The middle one is to enter the menu, which here you could see says menu, and it'll select which digit you are currently modifying. So hours, minutes, day, month, date, and then year. And I'm probably going to add more pages and more settings so you can change more functionality. The hours in this menu are in 24-hour mode, so you're just going to have to deal with that. I could easily do AM, PM, but whatever. And in order to actually adjust, you have to hold the middle button and then you click the up or down buttons how many ever times you want to increment this. So if I want to increase this to 20, I'd have to hold the middle button and click the up button here 5 times in order to increment it. And once you release that middle button, then it refreshes the screen. I figured this was the simplest way without if you couldn't implement a fast lookup table, and you had to be limited by a screen that takes like up to 3 seconds to fully refresh. If I did every time you clicked a button, it did a full refresh, that would take way too long. So I implemented this way, so at least you can kind of more quickly adjust. The up-down buttons, when you're not holding the middle button, will actually increment the position of the pointer, basically what's selected. And the quickest way, you can exit out by either clicking back when you're in the hours selected, or if you get all the way down to 24 and you click advance, then it'll exit out. The quickest way, honestly, is just to hit the reset button, and then it just kicks you immediately out of this menu. This pulling nearly just under 10 milliamps, that's not good. I can definitely get this down to the microamp range with just the microcontroller. The Eink display is powered via GPIO from the microcontroller, so it can shut that off completely, so that doesn't draw any current. And then it's just a matter of putting the main microcontroller to sleep, and that should be able to get me down to somewhere around like the 30 to 40 microamps range. Sorry. So that should make this battery last significantly longer. We're talking like going from like 2 to 3 week runtime to maybe like 2 to 3 years, something like that, off a full charge if you want to use this big of a battery. I plan on using a smaller battery that'll fit in the middle here, like a small pouch LiPo. And if I can get like 1 year battery off of something like that, I'll be happy. Even if it's like only 6 months and you have to charge this every 6 months, that's good enough for me. But yeah, I definitely need to work on the putting the microcontroller to sleep. I have libraries for that, so I don't expect that to be very difficult. But sometimes when you have other devices hooked up to I/O from the microcontroller, you have to be kind of careful about setting all outputs to high impedance in order to prevent like parasitic current draw, even if the microcontroller is in the sleep mode. So yeah, I'm gonna have to figure that out, how that affects the RTC. If I put the microcontroller to sleep, can the RTC keep running or what? I'm gonna have to figure all that out. So yeah, gonna have to do some experimentation and whatnot. But overall, yeah, this works just as a clock right now. Just the battery indication and like the lower power mode isn't implemented yet. If you guys are interested in building something like this yourself, either the PCB or the software, like I said in a previous video, I'm going to start charging for more complex builds that I've been making. So just shoot me an email. I'll probably just charge like a token, like $5 or something like that, for both the firmware and the PCB. So yeah, and once you buy them, you're welcome to modify them, use them in your own personal products or projects or products. I don't care by that point. But yeah, overall, this is actually turning out to be really cool. This is pretty, like, this is going to be a really good desk clock. It's like really high visibility. There is the I think it has a matte screen under this, but there's a protective film. You know what? Let's just pull the protective film off. There we go. It's slightly glossy, but it's actually mostly matte. Very good, like high viewability. It would be nice to make the digits a little bit bigger. There's a little bit room underneath there between the time digits and the day of the week. So I might be able to play around with some of the fonts, make them a little bit more visible or whatever. But yeah, if you guys have any suggestions for like added features or whatnot, maybe this is something that I will do a second revision on. But yeah, I've rambled on for long enough. Once again, huge thanks to NextPCB for sponsoring this project. And yeah, I'm really excited about this, making tiny little InkClock. Might 3D print some kind of case that'll fit. I'll have to desolder this header, obviously, and solder the battery. Find a battery that's thin enough to fit between and solder it inside, so that I can then design just a case that has cutouts for the buttons, and that's it. And obviously for the USB port. But yeah, this should be pretty tiny then, and you just sort of stick it on your shelf, and it'll keep time. And so anywho, love playing with Eink Displays. Definitely want to try implementing a quick lookup table for this guy. I'll do some research into that to see if anyone's come up with the values for the lookup table. That's something you'd have to do a lot of experimentation, and it's easy to destroy the screen, like permanently damage it. So it's not something that I want to, with only one screen right now, I don't want to experiment with and possibly damage this. But if someone else has come up with like a working LUT for this specific display driver, I am definitely interested in borrowing that to implement into this. So anywho, I'll see you guys in the next time. Bye.